Hello friends, welcome to my new video series on design of laterally unsupported beams. This topic is actually related to advanced design of steel structures, wherein we'll be discussing the things on how to design the laterally unsupported beam, what is lateral torsional buckling, what is the concept of shear center, what is warping, and all those things. So let's go further. So these will be the contents of this session. We'll have some about lateral buckling of beams, what are the factors which will affect lateral stability, what is the IS 800 Codal provisions, design approach, lateral torsional buckling of cantilever beams and continuous beams, effective lateral restraint, monosymmetric sections, non-uniform beams, concept of shear center, warping, uniform and non-uniform torsion. I have not included any numerical examples on this. We'll cover all those things in the next videos. Okay, let's start with this. Generally, beam resists transverse loads by bending action. That's an obvious thing. In a typical building frame, main beams are employed to span between the adjacent columns. Your main beams will be spanning between the adjacent columns, and the secondary beams will be actually connecting to the main beams. In general, it is necessary to consider only the bending effects in such cases because we have the loading in the vertical direction. Any torsional loading effects being relatively insignificant in beams can be ignored. The main form of response of a uniaxial bending of beams are listed below. This is actually given in IS 800 2007. Now the category 1, what is the mode of that is excessive bending triggering collapse. So this could be the one mode of failure, and the second category could be lateral torsional buckling of long beams which are not suitably braced in the lateral direction, that is unrestrained beams. You can see here this is the second category which we are very much interested in this session. So what does this type of category of beams says is lateral torsional buckling of long beams which are not suitably braced in the lateral direction. So this is the longitudinal direction wherein we have a loading here, and since these are not laterally braced in the transfer direction, so they undergo lateral torsional buckling. So you can see here failure occurs by a combination of lateral deflection and twist. So here we'll see those things in much detail in the further slides. And the third category is failure by local buckling of a flange in compression or web due to shear, or web under compression due to the concentrated loads. This is another mode of failure. And the last type of failure is local failure by shear yield of web. The diagram tells you shear yielding of the web, or it could be local crushing of the web, this second one, or the buckling of the flanges. If the outstanding width of the flanges is more and the loading is applied to the flanges, there could be buckling of thin flanges. These are the main failure modes of hot rolled sections, and we are interested in the second category, that is lateral torsional buckling. So we'll be discussing more on that topic now. Okay, coming to the lateral buckling of beams. In this section, lateral buckling of beams is described, and its close similarity to column buckling is also brought out to some extent. Now consider a simply supported beam here. You can see this is the simply supported beam, and laterally unsupported means there is no support from the lateral direction to the beam, only it is supported in the longitudinal direction, except at the ends, of course. Beams of short span, let us assume that this is the short span beam subjected to incremental transverse loads, means whatever loading we are actually putting this W, it is incremental, means it is not sudden, it is gradually increasing load at its midsection as shown in the figure. The beam will deflect downwards. You can see here in this diagram, you can see the beam will because of the incremental loading, the beam will deflect downwards, that is in the direction of the load. So the dotted line indicates the undeflected position of the beam before the loading, and this line indicates, that is this diagram indicates the deflected position after the loading. Okay, now this was actually the short span, and if I take into consideration a long span, what will happen? The behavior will not be same. A long span, when incrementally loaded, will first deflect downwards. You can see here, when it is incrementally loaded, this is a long span, same long beam I have taken, but it's a long span, and when subjected to incremental loading, will first deflect downwards, and when the load exceeds a particular value, that value we don't know, and when that load exceeds a particular value, it will tilt sideways. You can see here, it will tilt sideways due to instability of the compression flange, because there is no lateral restraint to the compression flange. So due to that, it will rotate sideways about the longitudinal axis. You can see here, this diagram is actually telling you first after the loading, first that beam will deflect downwards, and after the load reaches a particular value, it will tilt sideways like this, okay, because of the instability of the compression flange along the longitudinal axis, and because of the tilting, it will have some twisting effect on that. The three position of the cross section as shown in this figure illustrate the displacement and rotation that takes place at the mid section of the beam, and that which undergoes lateral torsional buckling. Now this phenomenon is actually called as lateral torsional buckling, wherein because of the incremental downward load, first the beam will deflect downwards and it will tilt sideways, causing some twist, and this phenomenon is called as lateral torsional buckling. Okay. Now if you see the same beam, the top, if the loading is downwards, the top portion of the I section is under compression and the bottom portion is under tension. The beam under transverse loads has a part of its cross section in the compression and the other part in the tension. That is the obvious thing. Now if you see this, why the lateral torsional buckling happens? The part under the compression becomes unstable, while the tensile stresses elsewhere tend to stabilize the beam and keep it straight. Now what happens? Because of the instability to the compression flange, the flange will try to move away, but because of the stability in the tension zone, it will try to stabilize the beam and keep it straight. So because of this stabilizing and destabilizing effect of the compression and tension flange, it will have some side sway. Thus the beam, when loaded exactly in the plane of the web at a particular load, will fail suddenly by deflecting sideways and then twisting about its longitudinal axis. You can see here. So this diagram is actually the elevation of the beam, and here you can't see any twisting effect, and when you see the plan, you can see the lateral translation of the beam has occurred because of the phenomenon of lateral torsional buckling. This form of instability is more complex compared to the column instability, since the lateral buckling problem is a three-dimensional in nature. It is not a two-dimensional anymore. The bending moment at which a beam fails by lateral buckling when subjected to uniform end moment is called its elastic critical moment. When the beam fails because of the lateral buckling when subjected to uniform end moment, and that moment is actually called as elastic critical moment, and that is denoted by the term M suffix CR, that is elastic critical moment. In case of lateral buckling of beams, the elastic buckling load provides a close upper limit to the load carrying capacity of the beam. Okay. It is clear that lateral instability is possibly only if the following two conditions are satisfied. Okay, so what are those conditions? The section possesses different stiffness in the two principal planes, and the second condition is the applied loading induces bending in the stiffer plane, that is, it induces the bending in the major axis. Similar to the columns, the lateral buckling of unrestrained beams is also a function of its slenderness. So slenderness is actually the length divided by the minimum radius of gyration, so that defines the slenderness ratio. As in case of buckling of columns, here also the lateral torsional buckling mainly depends on the slenderness. So there are many other factors on which it depends, so we'll see all those things one by one. Okay, now lateral torsional buckling of symmetric sections. When a beam fails by lateral torsional buckling, it buckles about its weak axis. You can see here, in this case, the I section is there and the weak axis is x axis and the strong axis is y axis. Sorry, it's a reverse thing. The weak axis is x and the weak axis is actually y and the strong axis is x. and when it is loaded to the end moment M, it will have the twisting not in the X direction, because that we call it as a bending, but it will have a twisting in the Y direction. That's why in case of lateral torsional buckling, it will have a bending in the major axis and the twisting in the minor axis. For the purpose of this discussion, the lateral torsional buckling of an I section is considered with the following assumptions. The beam is initially undistorted, it is because it is straight. Its behavior is elastic, because it means it is not cross the elastic limit, so that non-linear analysis will not come into picture. It is loaded by equal and opposite end moments in the plane of the web, because the calculations will become very easy. The loads act in the plane of the web only. There are no externally applied lateral or torsional loads, only end moments are there. The beam does not have residual stresses. Its ends are simply supported vertically and laterally. These are the assumptions what we have done to go ahead with the discussion on the lateral torsional buckling, because the calculations and the things will become very simple to start with. Okay. The critical bending moment capacity attained by a symmetric I-beam subjected to equal end moments. Equal end moments are these things, the moments which are applied at the ends and both are equal in nature but opposite in direction. They are actually called as equal end moments. Okay, the critical bending moment capacity attained by a symmetric I-beam subjected to equal end moments undergoing lateral torsional buckling between points of lateral or torsional support is actually a function of two torsional characteristics of the specific cross section. And what are those things? Those two specific things. The one is the torsional resistance and the other one is the warping resistance. We'll not go deep into this formula, because we also have to see these things in the further things. Okay, so I will not also look into this thing. Okay, now the lateral torsional buckling as stipulated in IS 800-2007, that is our Indian code for design of steel structures. New IS 800, that is the new edition, that is according to the limit state method, takes into account the effect of lateral elastic critical moment for consideration of lateral torsional buckling of beams, and stipulations are as follows. Simplified equation for prismatic members made up of a standard rolled I sections and welded doubly symmetric I sections is as below. So this formula actually gives you the elastic critical moment, that is the elastic critical moment is the moment at which the beam fails under lateral torsional buckling, and it is given by this equation. Now the first term, that is IT, refers to the torsional constant, and it is given by this formula for open sections. IW is actually called the warping constant. IY and RY as the moment of inertia and radius of gyration about the weak axis respectively. And the LLT is the effective length for lateral torsional buckling, which you have to consider, and it is given as per clause 8.3. HF is the center to center distance between the flanges, because and it is not the total depth. Remember, it is the center to center distance between the flanges, and TF refers to the thickness of flange. Most of these things can be found from the steel tables, and you can find out, and this is as per clause 8.2.1 of IS 800-2007. So if you go with that, let me just open that here. Okay, so this is the one where you can see this is the formula for elastic critical moment, which is given as per IS 800-2007, and it is given under clause 8.2.1. and if you go through this formula, you will come to know all the terms. So we'll come back to our slide mode.